Hey, so we're going to do another one of the 2019 AP Chemistry FRQs today. They are easily found by Googling the 2009 AP Chemistry free response questions. So I don't think you'll have any trouble finding it. And then you can look at it before you watch this video and you can actually attempt to do it. So a student is given 50 milliliters of a solution of sodium carbonate of unknown concentration. To determine the concentration of the solution, a student mixes the solution with excess 1 molar calcium nitrate, causing a precipitate to form. The balanced equation for the reaction is shown below, and we see the balanced equation, which gives us 1 sodium carbonate and 1 calcium nitrate, yielding 2 sodium nitrates, which stay in aqueous solution, and then calcium carbonate, which forms a solid or precipitate. Write the net ionic equation for the reaction that occurs when the solutions of sodium carbonate and calcium nitrate are mixed. So both sodium carbonate, Na2CO3AQ, and calcium nitrate, CaNO3 are in aqueous solution, as is the 2 sodium nitrates. And then again, we have that calcium carbonate as a precipitate. So anything that is in aqueous solution is busted up. So I got 2 Na plus AQ plus CO3 negative 2 AQ plus Ca plus 2 AQ plus 2 NO3 AQ, and then that's going to yield 2 Na plus AQ plus 2 NO3 negative AQ plus CaCO3 solid. I'm running out of room here. But when you look at this, what you'll notice is that the sodium is the same on both sides. The nitrate is the same on both sides, so we can cross those out. And so when it asks you for the net ionic equation, what it's really wanting here is Ca plus 2. It's customary to write the positive one first, CO3 negative 2. Like that. Okay, so that is the net ionic equation. The diagram below is incomplete, and I'm drawing the diagram as we speak here. And if you do this on the AP exam, you just draw right on the picture. You don't need to, draw it. And so I got an NO3 negative, Na plus, NO3 negative, NO3 negative. Got my precipitate down there. That's my solid CaCO3. Okay. So this is what's given to us. Okay. And it tells us that this is incomplete. And I don't know how many people, when I showed them, when they got showed this or had to do it on the AP exam, they immediately just paired it up with another sodium. Okay. And so, they thought, oh, well, we're missing some sodium. But what you need to think about is it said that the calcium was added to excess. And so all of the calcium was used up to make this precipitate down here at the bottom. But then, you wait till the reaction stops and then you add just a little bit more. So you have 1, 2, 3, 4 nitrates and 2 sodiums. And so you can kind of say, you've got that sodium and that nitrate going together, that sodium and that nitrate going together. You've got 2 nitrates left. And so they're trying to get you to think and see that it's not just going to be 2 more sodiums. If you added that calcium to excess, what you should have there is Ca plus 2. Because if you wanted to be sure that you got absolutely all of that carbonate in a precipitate, you added more of the calcium nitrate. So you should have a couple of calcium ions, or, well, in this case, 1, but you should have some calcium ions left over in that solution. C. Determine the number of moles of Na2CO3 in the original 50 milliliters of solution. So they give us the little table to do that, and that's actually not that hard. You start out with the fact that you got 0.93 grams of calcium carbonate, and then they tell you up there that 1 mole of calcium carbonate is 100.1 grams of calcium carbonate. And it says moles, we don't want grams. And then when I look at my balanced equation up there, I get 1 mole of calcium carbonate for 1 mole of sodium carbonate. So Na2CO3. So that's 1-to-1 calcium carbonate to sodium carbonate. So when I just work that out, 0.93 divided by 100.1. And so, since it's 0.93, I'm going to use 2 sig figs, and it's 1, 2, 3, 9.3 times 10 to the negative 3 moles Na2CO3. And so that was a pretty easy calculation. They gave us most everything we needed. And so since they gave us the mass there, we didn't need to spend time adding that up. And they wanted it in moles, and we didn't need to add up the sodium carbonate neither. So, yeah. But you see, we just set it up like a normal stoichiometry problem. So that was C. The student realizes that the precipitate was not completely dried and claims that as a result, the calculated Na2CO3 molarity is too low. Do you agree with the student's claim? Justify your answer. Okay, so this is one of the ones where you have to see whether the student was right or wrong. And there's no real predictability about whether you're supposed to agree or disagree with the student. In this case, you disagree with them. Because if there's water in the precipitate, that's going to tell you that you have too much precipitate. And if you have too much precipitate, that's going to translate to having a higher molarity of the sodium carbonate, because it's going to, if you have more mass of precipitate, that's going to translate to more moles of the precipitate. And since it's a 1-to-1 ratio, if you have more moles of the precipitate than you should, you end up having more moles of the sodium carbonate. Okay. E. After the precipitate forms and is filtered, the liquid that passed through the filter is tested to see if it conducts electricity. What would be observed? Justify your answer. It would conduct electricity because we've established that it has ions left in it. It's going to have nitrate ions, it should have some calcium ions in it, and it should have sodium ions in it. So now through E, hasn't been too tough. Now they get into a little bit of acid and base chemistry. The student decides to determine the molarity of the same sodium carbonate solution using the second method. When sodium carbonate is dissolved in water, the carbonate ion hydrolyzes to form the hydrogen carbonate ion, shown by the following equation. And we see a acid and base equation here, and we're given a KB statement. The student decides to determine first determine the hydroxide in the solution and then use that to calculate the initial concentration of carbonate. Identify a laboratory method, not titration, that the student could use to collect data to determine the hydroxide in solution. This one I remember people getting confused over, but honestly, if they don't want you to titrate, the other thing you can do is use a pH probe. And obviously, we haven't done that in the lab this year since we really haven't been in the lab this year for 20 and 21. But that's always an option, and I think we did do that virtually. So my answer would be you can use a pH probe. And then F, part 2, explain how the student could use the measured value in part F1 to calculate the initial concentration of CO3 negative 2. This one's going to be, I would say that's the thinker, and if there's one part to skip, I don't know how many points they could give you on this, but this one is a little bit more of a thinker. They don't actually have you do the calculation, which is good. But what you do is you make a nice chart, okay? And so you think that you have CO3 negative 2, and then water drops out, and then you have HCO3 negative, OH negative, and then if you put the initial CO3 negative 2 as X and HCO3 and OH as 0, you know that you got X and X plus X, and then I guess I'll make that Y. Because you can't have X and then have minus X, because then it would be 0, and you don't have 0. So you got Y minus X, and then you got plus X and plus X. And then what you could say is, in setting that up, the equilibrium concentration plus the concentration of the hydroxide would give you the initial concentration of the carbonate. So how I would answer that is, if the OH is found with a pH meter, it can be added to the equilibrium concentration of CO3 negative 2. And then if you wanted to get super fancy, you could say, if you got the KB, and then you would have HCO3 negative OH, and then you would have that CO3 negative 2 on the bottom, and then a little bit of algebra, even though we're not going to do the math because they didn't ask us to. Multiply both sides by the carbonate, then divide by the KB. And so that gives you CO3 negative 2 concentration is HCO3 negative, OH negative, which we have, divided by the KB. Whoops. And so you can see that would be, this is kind of a stopper problem because that would be a lot to think about, but there's no math, and then it's simple when you think about it, but that's one of those ones that if you're maybe a little flustered on the exam, that would be tough to think about. G. In the original sodium carbonate solution at equilibrium is the concentration of the HCO3 greater than, less than, or equal to the concentration of carbonate. Again, it says to justify your answer, and again, this could be one that would be frustrating for people. But you just have to remember that the Kb is a small number, 2.1 times 10 to the negative 4, and as the fact that the Kb is a small number, you're going to have more of the carbonate, the reactant, than you will of the product. And that's what they want you to say, is that Kb is small, you're going to have more of the reactant than you are of the product. The student needs to make a carbonate, hydrogen carbonate buffer, and is the sodium carbonate solution suitable for making a buffer with a pH of 6? Explain why or why not. And it's just not, because if you take let's assume that buffer had 1 molar concentration of the hydrogen carbonate, and which is the conjugate acid, and the carbonate, which is a base. That would make the pH of the solution equal to the negative log of the Ka. So we have the Kb, and so what I'm going to do is I'm just going to take the negative log of the Kb, 2.1 times 10 caret negative 4. And that gives me like 3.68. But that is the POH. So 14 minus my answer. So that gets me up to a pH of 10.3. So if I want to make a buffer solution that's a 6, I don't want to use this because it's going to give me a buffer solution that's much higher at about a 10. So this was a longer problem, but it took me a little while to explain it, but we still came in at about 17 minutes.